All right, we're gonna start getting started now. Hello, welcome everyone. Happy Valentine's Day. We're bringing another Intro to Tech on data structures. My name is Jacob, ACM's technical officer, and hope everyone's excited to learn some of the most important stuff that you're gonna be needing in your CS career. Okay. All right, so before we get started, please go. So some of our upcoming events right now is actually today, our ACM Valentine's Day social hosted by Paolo here in the back. You can wave, Paolo. Yeah, he's hosting a Valentine's Day social where you'll be able to paint ceramics and just get to meet a whole bunch of your other ACM family. 4 to 6 in this next door room, actually. So just right across here, the Travis room, 4 to 6. Please come attend right after this event. We'd love to have you. And then tomorrow is ACM-W's Python and Valentine's Day workshop. Where you'll be able to learn, I think, the basics of Python Turtle, and also, I believe, making Valentine's cards as well. That's tomorrow at the SCU 2.02.12 from 6 to 7. Tomorrow. And then the big main event that we're having is Rowdy Hacks, which is happening in, I think, not this weekend, but the next weekend. Our UTSA's biggest hackathon is happening then at SP1. It's called Rowdy Hacks, if you haven't heard of it. A hackathon is essentially you get 24 hours to create a project that gets judged based on different criteria or tracks that you sign up for. Usually you do this in a team environment. It's crazy big. There's a whole bunch of people that are going to come and compete. So you think you're one of the best coders that you can, please feel free to come to Rowdy Hacks. On top of that, there will also be sponsors and big companies that come as well, such as the Marathon, Petroleum, I can't remember the others. But yeah, lots of companies that you'll be able to network with and submit your resume to. Also give out free swag, t-shirts, buttons, pins, whole bunch of stuff that we got to offer for y'all. So I'm on the organizing team, and I can tell you that we're planning huge thing for Rowdy Hacks. So again, sign up is at go.rowdyhacks.org/register. I'll post it again in the Discord. It's also in the announcements channel. To sign up, you do have to RSVP, and we do take limited spots. But again, highly encourage all of y'all to come. So, and then the one you're all waiting for is the check-in to get your membership points. If you get 7 membership points for ACM, you get invited to our spring banquet where you get to network with some of our sponsors that sponsor ACM and then meet some of us as well. You can scan the QR here and sign in through our portal. And you also get eligible for like free swag, t-shirts and stuff. So we'd love to have you all as a full-time member here. All right, everyone's trying to look off from the phones now. All right, we'll move on. The check-in QR code will also be on the end of the slides as well if you forget to right now. So first of all, what are data structures? Data structures are essentially just a way of organizing a whole lot of data. If any of y'all have done coding right now, y'all may have worked with these things called arrays where they store a multiple of a certain data type. There are various ways that you can manipulate data. For example, a list of students for a classroom. Each data entry has its own specific criteria that may need to be stored, and data structures will help you choose how you want to store it. And we'll go over a few examples right now. For those of you that do know data structures already, do keep in mind I will not be going into big O notation, or for those that don't know, it's like runtime. You'll learn it in your future, but I'm not going to be going over this as this is more geared towards beginners. We're going to be rating them on our own scale from 1 to 10. So I think that we'll target more of a more general and intro dynamic. Again, these are meant to introduce people to the concepts, and each data structure has advantages and drawbacks. You are responsible for determining which data structure best fits each scenario. So again, each question you may be asked may require for a different data structure. It's up to you to determine which one, and we're going to go over some examples on which data structure will fit each. So to get into it, arrays. I'm sure anyone that started coding has learned about arrays at one point or another. They're in every single language. Usually one of the first things you learn. Arrays is actually a data structure. It's a way to store a whole lot of data. So before we get into that, this is what our memory looks like. This is where whenever we call an array, this is where it goes into our memory. It's basically a line of blocks. Each one of these blocks has a certain address. So for example, to create an array, we use like this code line, for example, int array, and then an array example. Your compiler or your code is going to basically go through this memory and find one spot that looks open and think, oh, this spot looks good, so we're going to start this right here. And then it's going to go through continuously go into every single next one and fill in the certain array, the array block or array element into that memory. Something to notice here is that it has to be continuous. It can't have one empty memory block in between. This is what basically what arrays are. Like, they have to be continuous. And then after you create the array, it gives a pointer to the first element of the array. So now accessing, for example, say we want to get the third index of the array. The computer is going to look at this array variable and create a memory pointer there, and then it's going to count the amount of indexes. So 1, 2, 3, and this is going to return 4. It's going to start at the beginning and then go all the way into the one you need. This is also what is known as direct access, because the computer is way much faster at counting from 0 to 3. So it can very quickly get this fourth element right here because it starts from the beginning and then needs to go +3 to the next memory spot. Adding and removing elements are not exactly possible because an array is a fixed size. Again, it has to go into these 4 memory spots. There could be other memory spots, or memory could be elements. Anything different can be in these other memory spots. You've only reserved these 4 for the array. So adding or removing elements is not really possible. You can only change the values. And here's the table that we'll be seeing a whole lot of. This is our ranking of how we're going to do data structures right now. So right now for space, I'm going to give it a 1 out of 10 because it has to be continuous. Say for example, we have an array of say 100. It has to find a memory block that has 100 free spaces. And when our memory gets really, really big, say like 1,000 or 10,000, it's going to get increasingly difficult to find in an open spot of that much. For our access, able to get a certain element in this array, I'm gonna give out a full 10 because you can't really get much faster than being able to go from the very beginning and then go the certain amount of index numbers to the array that you're looking for, to the element that you're looking for. And then I just negligible did add and remove because you can't really do that. So some uses for array is whenever you're storing the same data type and you know you need to access that stuff really fast. Also, it's good for small groups because you can't really store lots of data in an array. So next we're going to go to linked lists. Linked lists are like arrays, except the difference is that they don't need to be stored in continuous memory. You can see here that each node, we're going to call these nodes, each little block has a data, what it's going to store, and then what's usually called the next pointer is where it points to the next node that it's looking for. You can hear the memory again. An example of where these blocks will fall in memory is it can be literally anywhere that they want. But you know that with the arrows, it's going to point to the next array that it's looking for, or the next node that it's looking for. So you always know that 1 is going to point to 2, and so on, regardless of where it is in memory, because there can be holes. There can be holes in here. So the difference between that and arrays is that it does not need to be continuous. It can go to anywhere in the memory that it wants and point it there, and the next pointer will tell you which one it's going to go to. However, the downside I guess first of all, you can add things to this. It's a list. You can just create a new node and say, let's do a new node 5, and then have the next pointer point to the next one. Same with removing. You can easily take one out. So for example, take out 3, and then tell 2 to point to 4 instead. So adding and removing is a whole lot easier. It's one of the upsides over arrays. However, access though, it's going to be a whole lot more time consuming, a whole lot more difficult. For example, let's say we want to get to the last element of this linked list. We had to start at 1, and then it has to follow the next pointer to navigate where's the second one. All right, second one's here. All right, now we can go to the next one. The next one's 4, and the next one's 5. That's going to take a whole lot longer, especially whenever your data gets a whole lot bigger. So imagine having to go through this next pointer 100 times or 10,000 times if your linked list contains 10,000 elements. So for this chart now, I'm giving space a 10 out of 10 because it can literally be stored anywhere. Doesn't need to be continuous memory. It can easily find random spots in memory to put these nodes. However, access is going to be a whole lot more difficult because you never know how long it's going to take. It has to go through each node at a time. It can't easily count 5 spaces from the first memory slot. And now adding and removing are also going to be a lot easier. I'm giving it a 4 out of 10. So because I think it's possible now, but you still need to be able to track to or access to that element and remove it or add it. Next up is queues. So queues, we're gonna be using this node structure a whole lot more. So for example, I'm sure y'all have heard of like a queue before, or a line, like a line of people. Say like at a restaurant, you're waiting in a line. Usually, if you're the last person in the line, you'll be the last person to get their order taken. So this is the idea of first in, first out. If you're the first person into the queue, you're gonna be the first person out of the queue. If you're the last person in, you're gonna be the last person out. So there is an order at which you access this data. The idea of enqueuing and dequeuing is basically adding to the queue and then removing from the queue. So we'll see a code example here shortly. So for example, we're gonna over here on in queue data 1. So we're gonna add data 1 to the queue. For example, do this. So we create a node and we're setting this in the queue. Now I'm gonna enqueue data 2. So now we added node data 2, and we're having the next pointer pointing to data 2. So this is the order that we're going to follow this data 1 and then data 2. Enqueue data 3 again, you're going to add the data 3 node. And now to dequeue, since data 1 was the first one in, that's the first one that's going to get dequeued. So for dequeue, data 1 is going to be taken out of the queue and processed. And we're going to dequeue again, data 2 is next. So data 2 is going to get dequeued. So now we're just left with data 3. So now we're going to enqueue data 4 to add 4 to the end of the queue. So right now data 3 is currently the next one to be processed is front of the line, and then data 4 just got added to the end of the line. We're going to enqueue data 5, and then we're going to dequeue, and data 3 is going to get taken out because it was next in line. And this is what our queue is left with after this process. You can only add to the end of the queue. So anyone that gets added is going to be processed last because you only remove from the front. So this is the idea of first in, first out, and we're going to see some changes of this as well in the future. Doing it on time. All right, doing good. So here's our chart again. So space again, 10 out of 10. We're going to be using this node structure again, where you can put nodes anywhere you want and use these next pointers to point to the next nodes that they're going to. Access is also 10 out of 10 because if we remember in the arrays, it's really easy to access the first one. So since the front of the queue is always going to be the one that we're looking for, we're going to give it a 10 out of 10 because that's always the first one. Adding is kind of difficult because again we have to go to the last one. I have to go through all those next pointers again to add to the end of the queue. But again, removing is going to be a whole lot easier because again always removing from the front. So that's always going to be the first one, and yeah, always removing from the front of the queue. So since that has to be the quickest, we're going to give it a 10 out of 10. So I'm sure y'all are seeing now a pattern of how we're accessing these data, and we'll go over this more in the future. So stacks, basically the opposite of, I forgot to remove this code. So basically the opposite of queues, where instead of being first in their first out, you be the first and last out. So think about you're holding a stack of books. If you put stuff on top of each other, it's it's really difficult to remove the bottom one, the first one you put on. Usually it's a lot easier to remove the top one. So this is the difference between pushing and popping. You can push things onto the stack or add things to your stack, so it's at the bottom, and then as you push stuff onto the stack, then you can pop it off or remove the top one. So if you're the first one in and you start stacking stuff on top of it, you have to pop every single one from the top and until you can access the first one again. So first in, last out. So another code example, we're going to push data 1. So now data 1 is on top of the stack. Push on data 2. So now it's data 2 is on top of data 1. Add data 3. And now to pop, since data 3 was the last one in, it's going to be the first one out. And vice versa, data 1, since data 1 is the first one in, it's going to be the last one out. So we're going to pop off data 3 because that was the most recent one. We're going to pop off data 2 because that was the next recent one. And then poor data 1 is not going to get popped off yet, so we're going to push data 4 and then add data 5 to the top of the stack. And then going to pop off the last one, so data 5 is going to get taken off because of the last one in, and this is where our stack is left with. If we were to pop 2 more times, data 4 would go next, and then data 1 would go next. This is the difference between a queue and a stack. Queue is first in, first out. Stack is first in, last out. You only add to the end, so you only add to the end of the stack, and then you only remove from the end as well, so you remove and add from the same spot. Space is, well, we'll give it a 10 out of 10 because again, it's a node structure. Access is much easier as well because you're always going to last. Usually you have a pointer to the top of the stack, or sometimes you can have a pointer to the bottom of the stack, and then it gets a lot harder. But usually for this example, we're going to be doing the top of the stack. So again, adding is to the top of the stack, and then removing the same thing. So next thing, get a little more complicated, trees actually. So trees, this is an example of a tree. That's not good. Uh-oh. Sorry, Horjal. Hope not. Did it turn off? Oh boy. Sorry guys, this just didn't happen. Sorry, stream chat. We lost the projector and we're trying to fix it right now. So I guess while we're fixing this, anyone have any questions so far? Everyone good? Anyone lost? Is everyone lost? We all good? Everyone understand everything? All right, cool. Oh, we're good. Yes.
I mean, if you add like for the stack and the queue, yeah, like first in, first out, and first in, last out. Why the loop is like 10 out of 10? I still don't understand. Like
Because usually, whenever you for queue or for stack.
for stack.
For stack, because usually we have a pointer. Oh, here, I'll see. Show it again. All right, yeah. Actually, I think we should change that to 10 out of 10 for add as well, because usually you have you have the pointer that points to the end of the stack. So again, since that's always the first one that we're accessing, that's why it's a 10 out of 10, because it's really easy to access the first one instead of having to traverse like through all of them. Honestly, this should be 10 out of 10. That's my bad. Yeah, put 10 out of 10 for add on those notes. I'll change it in the slides and when I post them. All right. All right, so trees now. Now that our projector's not cut out, so trees are another way of organizing data. It's a bit different from the linear thing we've been doing before with queues, stacks, and arrays. You can see that these data is like they'll have multiple things that they point to. So for example, data 1 is pointing to data 2 and data 3. Data 4 is pointing to 5, 8, and 10. So this is really useful for, like, say, hierarchical trees, maybe like family trees, just data you want to store in a tree style, or maybe like a file structure. So whenever you access your files, say your C drive is at the top of the tree, and then as you navigate through more folders, you can get subtrees. Each node has its data and any number of child nodes. So for example, data 1's child nodes will be data 2 and data 3. Data 4 child nodes will be 5, 8, and 10. This is how we label the nodes in a tree. Some more examples of trees. Actually, before I get into that, trees are special because they store their data in a very special way. They usually by sorting or by a minimum or a maximum. Usually they aren't as random. And the special thing about trees is that they usually come with their own algorithms to basically sort them or to add and remove them. Some examples of these trees are binary trees. Binary trees always have at most two nodes to them. So, two children. So they can only have 0 children or 2 children. Ternary trees, where they can only have 1, 2, or 3, or n-ary, which they can have any number of nodes. These are just the different ways to label trees. Binary search tree is another way to store data. For example, in this example, 8 is at the root. Anything less than 8 will be on the left child. Anything greater than 8 will be on the right child. And you can see for every single node, that's the same case. For 3, 1 is less than, and 6 is greater than. This makes it really easy to find a value that we're looking for. So for example, for searching for 6, we know 6 is less than 8, so we're going to the left child. We know 6 is greater than 3, so we're going to go to the right child, and there's 6. So binary search trees are making it a lot easier to search for your algorithm. Instead of, for example, an array, you have to go through every single one to try and find what you're looking for. Red and black trees, this is a really complicated one. This basically is a self-balancing tree, or a way to basically, and you can use algorithms to find whatever data you're looking for based on if a node is red or black. You'll be learning more about these in the future. These are really complicated, but just another example of trees. An AVL tree is another basically self-balancing tree where it makes it really easy to sort your data. The special thing about AVL trees is that there can't be a node difference between every level of greater than 1. That's not really complicated. I don't really have time to get into right now, but in the future, we'll learn about AVL trees and how they're special. And then heaps. Usually these are minimum and maximum heaps. It's a whole lot like binary search trees, except instead of the root node being the middle, it's the top node is always the smallest or the biggest. For example, in the minimum heap, 10 is the smallest out of all the data, and then maximum, the 100, is the biggest. So these are different ways to store data in a tree-like structure, and each one of these comes with their own algorithms to basically maintain their data and to maintain what keeps them the type they are. For example, if I were to add 110 to the max heap, then the tree will use an algorithm to basically reorganize itself into create a 110 to be at the top of the tree. I can't really get into the algorithms right now, but I know in the future you'll learn some of these. So back to our tree. Here's our chart again. 8 out of 10 for space because there's gonna be a lot of nodes. Each one has to have their own different children nodes that tell them which one is their children, and that's gonna create a whole lot more space. For example, whenever you're storing a whole lot of data. Axis is we're gonna give out 6 out of 10 because it's, for example, that binary search tree. It's you don't have to go through every single node. You just have to know which child node to go to. Same with adding and removing. You have to know you can easily go to go down a certain path to add or remove the one you're looking for. Now to get things even more complicated are graphs. So you can kind of see the similarity between this and trees, except this isn't really a tree-like structure. It's just kind of a mesh structure. So the thing about graphs is nodes can point to whichever one that they want to. They can point one direction, or they can also be bidirectional as well. They can point to each other. So for example, if we look at data 5 is pointing to 4, it's pointing to 3, and it's pointing to 6. So a good example of a graph is think about like a city, for example. Every single intersection can be a node in that graph, and all the paths, for example, think of downtown campus or downtown San Antonio, where there's a whole bunch of one-way streets that you never know which one you're going to go down. You can use a graph to visualize that. You can only one-way path to get from one intersection to another, and then determine where to go from there. The special thing about graphs and what they are used for is what's called pathfinding. If any of you ever have done games and heard about the idea of pathfinding, is they're navigating, like knowing which way to go. So again, that downtown example, you need to know which intersections to take, which paths to take. Pathfinding algorithms can help you navigate a graph. For example, to get from node 1 to node 7, you can take from 1 to 3, and then 3 to 6, and then 6 to 7. That's an example of a path that an algorithm will find for you. So if you're ever storing like stuff that has multiple like paths and needs to go from whichever directions, it's a lot easier to pathfind with graphs. Space, again, the same thing as before. There's gonna be a whole lot of nodes, a whole lot of paths to store, and it's gonna be a lot more powerful or a lot more needed for space. And I didn't really put anything for access, add, or remove because you can't really access one thing at a time. It's usually meant for, I guess, usually these nodes get also stored in another data structure, for example, an array. Usually create an array of all of these nodes so you can easily access them at a time, but that's up to you what data structure you want to use for either an array or a linked list or whatever. But another way to visualize the graphs, or use another way to store all the elements so you can access which one you want, is an array. These are really complicated. I can answer some questions if you have after the workshop, but this is really all I have time for the graphs. And then the last one we're going to talk about is hash tables. Hash tables, I think, are the most useful data structure. If y'all remember arrays, arrays usually always had an index or an integer that allowed you to identify which node you're looking for. Hash tables are special because instead of always using an integer index, they can be whatever you want. For example, in this example, we're going to use a string. So if I want to access data 1, I need to give in the string ACM. It can be whatever you want. As a key, it can be a string, it can be a character, it can be an integer again if you want. It can be like an ID or whatever you need. For example, the example I've been taught is a parking garage. If you want to go park somewhere, each parking spot has, let's say, a string that corresponds to that parking spot, and then a boolean to know if it's open or closed, or sorry, taken or not taken. You can use a hash table to store these parking spots. For example, if I want to pull this parking spot 1042, I can use this hash table to look for the key 1042 and then get the boolean whether it's open or closed. I have another coding example. You're going to use the function get to basically open or find the contents of our hash table. For example, this first one, get ABC. So we're going to be looking at this hash table, and then it's going to find ABC, and then it's going to know this is the one we're looking for, and return 2. The next one, get the key Liam. We are going to scan the hash table and look for the one that matches the key Liam. We're going to find it right there, and then return the corresponding data, and that's 3. And then the last one, get car. We're going to scan the hash table, look for the key car, and then let's find it right there, and then return the data 5. So here's our table again. I give a space and 8 out of 10 because all I need to store is the key and the data. It's a lot much more easier to store. Access is usually really easy because you can it's able to quickly scan whichever, the computer's able to quickly scan all the keys and know which one is which. And then same with adding or removing. It's really easy to just add a new one on the end. For example, we went to linked lists again, where it's really easy to just add one to the end, create a new node and then add it or remove it. And that's essentially hash tables. And that is actually all the data structures that I had for y'all. Those are the concepts. Those are the most common data structures that are usually seen in your coding interviews. You'll learn more about like the runtime complexity and stuff like that. And yeah, that's essentially all I have for y'all. If you have any questions, I'll be here for next little bit to answer any questions I'll have. If y'all missed the check-in, here's again. Also go to portal.acm-USA.org to sign in again, and thank y'all for coming and listening. So anyone have any questions or any help with anything? Any other misunderstanding? Yeah.
Do you have any specific language using the data structures? Because I know for C we have like pointers, so it's like pointing to the address.
The special thing about C is that like they make you code your own pointers. Usually in every language, like they all have their types of pointers. You just don't see it in the back. For example, Java, there are linked list objects and hash table objects, but they're all stored the same way. They all have pointers that point to each other. You just don't see it because it doesn't want you to manipulate it. That's the special thing about C is that it makes you do everything. Sorry? Yeah. So structs are like a way to store data. Yeah. But you can code these in any language. That's why I didn't give any coding examples, because honestly, you don't really need to know how to code them. They're the same thing as anyone else's coding. You can look it up on the internet and find how to add to a linked list, and you'll be able to find it really easily because again, it's all used the same thing. It's just knowing how to manipulate this stuff and knowing which data structure to use for your given scenario. Because you're not gonna be able to use like for that intersection example or a city, you're not going to use a linked list because you can't store the paths easily, knowing which node to go to. So a graph will make more sense. So the data structures are really just knowing which scenario calls for what data structure. But as for languages, they can be coded in any language.
Like from C, and then if we switch to another language, I have no idea which to.
Yeah, that's where it's really helpful to read like those languages docs. Usually, most high-level languages, they already come with libraries that have those data structures pre-implemented already. Like the methods I use, like push, pop, enqueue, dequeue, and that get for hash tables. That's usually the common practice for when manipulating or using those certain datas. You'll learn all those common practices in future classes, or again, if you read the docs, they'll tell you which functions to use. Y'all welcome to grab some snacks in the back. There's chips and drinks. Yes. Yeah.